In this talk, we introduce deep imitative reinforcement learning for temporal logic robot motion planning with noisy semantic observations. So our general goal is to make the robot to learn how to accomplish high-level tasks. There are a few challenges of doing this. The first one would be noisy sensing input. For example, if the sensor detects an object like this, and we're not sure if it's a condo, or a bar, or a solar panel, then our challenge is to plan efficiently, because the robot has to do sensing, planning, computing, and executing at the same time. So we'd like to design an efficient algorithm to respond to environmental changes quickly. We use linear temporal logic to specify the task. In general, it contains a few basic logical operators. For example, true, atomic prepositions, or, not, next, and till. For example, this LTL specifies the robot to visit A first, and then visit B, never go to C at all time, and eventually stay at T forever. To check if a robot satisfies this LTL specification, we can convert it to a graph, which is deterministic Rabin-Thompson. It contains set of initial states, set of states, input alphabet, transition relation, and set of accepting pairs. For example, the graph on the right-hand side corresponds to the LTL, saying that the robot needs to visit A first and then visit B. We can track the A and B down from the transition relations on the edges. So the robot needs to visit A first and then visit B to get to a accepting state. Or the robot can visit A and B at the same time, meaning that these two labels referring to the same objective. And we model the robot dynamics as the labeled Markov decision process. The only thing that this one different from the regular MDP is that we define labels over all the states. There have been some existing works that can solve MDPs with known transition probabilities. In general, they take a product between the DRA and MDP to generate a product MDP. And then we need to run AMAC decomposition to determine the accepting states of this graph. So these methods usually assume known transition probabilities, which is not the case in real-world scenario. And it's inefficient because running AMAC decomposition requires high computational complexity on such a large graph. And also, AMAX doesn't always exist. There are some other works using reinforcement learning to learn the transition probabilities in MDPs. In general, they explore the environment using some exploration policy and then gather training data, add them to the buffer, and then run the reinforcement algorithm to train. In general, the reward functions are designed like this. They give a positive reward for states needs to be visited infinitely often, and negative rewards for states that need to be avoided. But the problem of this is the training is inefficient during the early stage. And also, the actuator noise is considered, but sometimes the sensing uncertainties are not considered. So our goal is to design an efficient reinforcement algorithm to tackle sensing and actuation noise at the same time and try to incorporate previous environmental knowledge into training as much as possible. And we propose to hire experts to guide the training process. For example, we can fine-tune on top of the former experience, and in the meantime, we can learn to minimize the effect of uncertainty. So, in general, imitation learning can solve this problem. They hire an expert to generate some demonstration data and then run supervised learning on the demos. This is useful to warm start on the training, but it requires human interactions, and the policy cannot perform better than the experts. Instead, we use product-based model checkers to give suboptimal solutions, and then using reinforcement to refine these solutions to optimal ones. So, this process will be fully automated, fast, not human dependent, and unlimited amount of training data can be generated. Specifically, we model our sensor as a label transition system. Labels are reconstructed from sensing inputs in real time, meaning that every time there's a new sensing input, it will overwrite the old ones. And then we take a product with DRA. As we will introduce later, we usually use a much smaller DRA in this time, and it only contains 2 to 3 states. So we use existing product automata-based model checker as an instructor to give suboptimal solutions. Then we design a DIQL algorithm to refine the suboptimal solutions to the optimal ones. First, we need to generate a globally optimal Robin sequence. This can be done by running any model checker and then project the resulting path onto the Robin state space. And in the paper, we show that this should be unique and optimal because it only depends on the LTL. First, the robot decides to take instructions or not by some probabilities. And if yes, we generate the instruction and put it into the training buffer. If no, we just run regular exploration policy and then put the S prime R tuple into the training buffer. So here's how we specifically generate instructions. Assume we are currently in MDP state S3 and DRA state Q2. We first need to locate Q2 in the optimal Robin sequence. And in this case, the optimal sequence will be 2, 1, 0. So Q2 corresponds to state 1. And considering state 0 is the accepting state, so we need to pull out the transition relation between state 1 and state 0 and set it as the new local LTL, which will be then converted to DRA and then take product with the LTS to give instructions. So now we show our results from numerical experiments. We run the algorithm on a 10x10 grid wall, which looks like this. And because we consider sensing uncertainties, so maybe the map reconstructed from the sensor looks like the bottom one. And there are 5 actions the robot can take. And also we assume noisy robot actuator. So this video shows how the robot accomplished this LTL task. It first heads towards A, B, and T sequentially, and then circulating between A and B infinitely often. Now, this reward episode curve shows our algorithm outperforms odd baselines. The main reason is that the suboptimal solutions are helpful to increase the training performance at early stage. In general, we develop a Deep Imitative Q-Learning method that can refine suboptimal solutions provided by product automata-based model checkers. It can jumpstart the training in very early stage, and no human interactions are required. So it means that a limited amount of demonstration data can be used to boost the training performance. And also, we show completeness proofs in the paper. In general, if a policy exists that maximizes the probability of satisfying the LTL, then the imitative learning algorithm will find it with probability 1. Thank you for listening.